Okay, so with example 2, we've got a ladder AB. Okay, I'm just going to put it in there, AB with a mass M, length 3A. I'm just going to go through and highlight some of this important information. So I got mass M, length 3A, rough horizontal ground. The other end, B, rests against a smooth vertical wall, mass 2M, fixed ladder point C, where A to C equals A, angle of 60 degrees. That's pretty much all the really essential stuff there. Okay, so we put that in here. So we've got horizontal ground, 60-degree angle. Okay, we've got about the midpoint of our ladder. That's not really, so that should be more straight going down, but there you go. We've got a mass of 3 of M, mg, and that's about 1.5 A, okay, because we've got a length of 3A altogether. Then we have another mass coming down, which is 2 mg, and that's A meters from A, and that means that's 2A. C is 2A from B, okay. We also have a smooth vertical wall, so no friction at the wall, but we do have some other forces which are acting in here. So firstly, we've got a reaction force at A, and we then have a reaction force at B, and that acts perpendicular to the wall, because it's always perpendicular to the surface, okay. We have a friction force at A as well, so that's F equals friction times by RA. Okay, and I think that's it for the forces so far. Okay, so there we go. There's our scenario. All right, so from here, I find it easy if I just kind of with some of these questions, if you just go through and write down everything that you know first, and that should help you find the stuff that you don't know or how you find it. So what I'm going to do start off by doing is just resolving vertically. Okay, so with my resolving vertically, I've got a 2 mg weight coming down here, and another 1 mg, and then a 2 mg. So I've got mg plus 2 mg, okay, and then my other vertical component is Ra. Okay, so that has to be equal to Ra because they're opposite and equal. So therefore, Ra should be equal to 3 mg. All right. The next bit is that we can then resolve horizontally as well. And if we do that, we can see that Rb, reaction force B, should be equal to friction because they're the only two horizontal components. Okay, which means that Rb can also be written as Ra times by our coefficient of friction. All right. The next bit is there's obviously lots of unknowns in here, so lots of things that we don't know. So we need to take a different strategy to work out our coefficient of friction. So the next thing I'm going to do, I'm going to take moments, and I'm going to take moments around A. Okay, so taking moments. Now you could take moments around any of these points. I like to use A because I find the angle, that 60-degree angle, kind of easier to work with because I know that one for sure. Okay, so if I take moments around A, then my first thing that's acting on A is that 2 mg force coming down at C. That's an A distance from A. Okay, so I've got 2 mg times by A, because I've got a distance of A, times by, now it's the perpendicular, remembering that your moment is the perpendicular distance from your pivot point. So my pivot's here. My perpendicular distance is the distance between the pivot and the right angle. Okay, so to find that distance, I already know the hypotenuse is A, but to get that I need to times by cos 60. Okay, plus, now this would be acting in a clockwise direction. I also have this force of mg, which is also acting in a clockwise direction. So mg is 1.5 A from the pivot. Okay, and again, I've still got cos 60, okay, because I've still got that 60-degree angle, so I'm timesing that by cos 60 to find the perpendicular distance, and I'll just draw it in there in a different color so you can see it. So if I followed this mg down, perpendicular distance would be that line there. Okay, now because I know that this is in equilibrium, my clockwise and my anti-clockwise have to be equal. So the next thing that's acting on it is this force Rb, and that would be pushing in an anti-clockwise direction. So Rb is 3a from the pivot point. The fourth is RB. Okay, and the perpendicular distance. Now this one again is a little bit tricky. So if I follow RB along, this length here, that would be my perpendicular distance from RB. So I'm looking at that length there. So my angle in this triangle, that's 60 degrees because it's parallel to the horizontal. So that's 60 degrees. So I'm looking at sine of 60. So I then need to also times by sine 60. Okay, so there's all of my stuff that's happening. Okay, so from here we can simplify this a little bit. So we've got 2mga cos 60 plus 1.5 mga cos 60 again, and that's equal to RB 3a sine 60. Okay, so there's all of that in together. Now we've got 2mg cos 60 and 1.5 mga cos 60, so I can add those together because they're like terms. So I end up with 3.5 mga cos 60 equals to RB 3a sine 60. Okay, so I'm just going to move my page down a little bit. Okay, so from here, now if I go back to looking at my resolving horizontally, I know that RB equals to RA times by the coefficient of friction. Now this is what we're solving for. We still don't know what RA is, but I do know that RA is equal to 3mg. So if I want to, from this point, I'm going to divide RB by 3a sine 60. So I've got 3.5 mga cos 60, okay, that's my left-hand side, divided by 3a sine 60, that's my right-hand side, okay, divided by that. I'm going to sub that in for my horizontal resolved equation. So 3.5 mga cos 60 over 3a sine 60, okay, and I know that has to be equal to RA, which is 3mg, plus my coefficient of friction. Okay, from here, I've got a couple of things that I can do. So, oh, sorry, that should be, sorry, why did I add? That should be multiplied by times by coefficient of friction. Okay, so from here, I know that 3mg times by the coefficient of friction equals to this. Okay, so from this, I've got lots of the same variables, so I should just be able to go through and kind of do a fairly straight solve. So I can divide through by, firstly, I can divide this fraction through by a. I probably should have done this earlier. Okay, so I can divide that through by a. So I've got 3.5 mg cos 60 over 3 sine 60, okay, equals 3mg times by coefficient of friction. Okay, now I might so from this point, so I'm just trying to think about whether I want to put it in exact values or not. I don't think I really do for the moment. So what I'm going to do is I'm going to divide through by mg, because you can see you've got mg on both sides of the equation, so I can divide that through by mg. Okay, and I end up with 3.5 cos 60 over 3 sine 60 equals to 3 times the coefficient of friction. All right, now I can divide through, I should be able to divide through by 3. So I'm just going to change this to a 9, cancel that out. So my coefficient of friction is equal to 3.5 cos 60 over 9 sine 60. All right, now I'm just going to chuck that in my calculator. I'll be back in a second. Lovely. So I work that out and I get 0.2225 as my coefficient of friction. Okay, perfect, that's done. All right, we'll start on the second part. Oh, so I just looked at part B, and it's you don't actually do any calculations. It just says state how you use your assumption that the ladder is uniform in your calculations. This should be hopefully fairly self-explanatory for all of you. Obviously, the ladder is uniform, means that you can assume that weight is at the midpoint. Okay, so you can assume that mass mg is at midpoint. Okay, and you might even want to put that that's 1.5a. Okay, and that's it. All right, easy done. Okay, we'll start on the next bit in a second.